Hi, ladies and gentlemen. We are continuing our discussion of modern physics and about the dual nature of light, about how light is a particle and a wave, and about how, as a particle, it can do many things that particles do, even though it technically does not have any mass. It's made out of pure energy. But even though it's made out of pure energy, it can still collide with something and knock it out. Now, we had previously seen in the photoelectric effect, the energy of the photon strikes an electron and gets completely absorbed, knocking the electron out. But the energy of the electron does not have to get completely absorbed every time. If we look in this model over here, we have yellow light, which strikes an electron. During the collision, it gives off some of its energy and gives up some of its momentum. In fact, because it is a collision, we still have the idea of conservation of momentum. But if we apply our original ideas of momentum, P equals mv, to this collision question, it's not going to work. Because as I previously mentioned, photons have no mass. They're made of pure energy. But scientists were able to calculate the momentum of a photon nevertheless, realizing that the momentum of a photon isn't based on its mass and its speed, because technically it has zero mass, and the speed of light, well, no matter what color it is, it's always going to be 3 times 10 to the 8th meters per second. But they managed to calculate that the photon momentum is inversely proportional to its wavelength, or really its frequency as well. Okay. So when we do a collision question with photon momentum, we just have to use our original ideas for it. Well, if we go back to this question over here, we know that yellow light had struck and was able to give off some of its energy to the electron. So if we approach this like any previous momentum question, we can always set up a before versus an after. Before, we have an electron that technically we'll say isn't really moving anywhere. And we have yellow light that's approaching the electron. Okay? So we have momentum 1 plus momentum 2, which, well, technically crosses out. And it's going to, afterwards, the yellow light loses some of its momentum and turns into red light, actually. Okay? And the electron is now traveling somewhere with a certain speed, certain amount of momentum. The question is, how fast is it moving? Well, if we were to use this as a straight momentum question, this isn't really an ideal picture because momentum is really a vector. So we would just need to make sure that we keep that in mind, that it deals with X and Y axes. But if we do solve this question over here, we realize that H over lambda 1 will equal to H over lambda 2 plus mv. Okay? So the photon loses some momentum and gives it to the electron itself. Because it was yellow light has a wavelength of about 5.9 times 10 to the negative 7. So mv, we can say in this case, of the electron is equal to H over delta lambda, meaning however much the wavelength changed, then that will be based on how much momentum it loses and how much momentum it ends up giving to the electron. So the amount of momentum it gives to the electron, okay, will equal to 6.63 times 10 to the negative 34 joule seconds. Notice I'm using the joules version of H, simply because momentum is more of a mechanics idea that deals with energy, joules. It doesn't really deal with electron volts. Divided by, well, if I subtract my two wavelengths over here, the wavelength of yellow light, red light is 6.67 times 10 to the negative 7 meters, minus the wavelength of the yellow light, 5.88 times 10 to the negative 7 meters. I can find that the momentum of the electron is equal to 8.39 times 10 to the negative 27 kilograms meters per second. Now, if I want to solve the velocity of the electron, the velocity will simply equal to that number divided by the mass of the electron, which is 9.11 times 10 to the negative 31, and the velocity of the electron would be 9,212 meters per second. Okay, so this is one way of solving for the speed of the electron after a momentum collision. And the last thing I want to mention is with regards to the formula P equals h over lambda. Well, what's the unit for P? What's the unit for momentum? Originally, it was kilograms meters per second, but that isn't really going to work, of course, for light, for photons, because they have no mass. So instead, we'll base it on the formula itself. So the unit is going to be joules seconds per meter, okay? And for those rare occasions, we use the electron volt version of H. And it could also be electron volt seconds per meter, okay? Now, the idea of photon momentum got taken one step further, okay, by Louis de Broglie, who started thinking about things. And the fact that light had recently been discovered to have both particle properties and wave properties, well, he started thinking to himself and he realized, well, perhaps all objects in nature have particle properties and wave properties. In fact, if you took our original formula for momentum and set it equal to our new formula for momentum for photons, then technically we could solve for the wavelength of any object based on this formula. Okay? In fact, let's try it right now in question 21. If you want to figure out the de Broglie wavelength of a 0.2 kilogram ball moving with the speed of 15 meters per second, lambda is equal to 6.63 times 10 to the negative 34 joule seconds over 0.2 kilograms times 15 meters per second is equal to 2.21 times 10 to the negative 34 meters, which is a very, very, very tiny number, meaning that we all have some sort of wave properties, but it's just too tiny to actually see. But what exactly is holding us back from, well, being able to observe our wave properties? And the fact is, it's our mass. Anything that has too large of a mass is simply going to have too small of a wave function to notice. So de Broglie started thinking, well, if objects that have too much mass have too little wavelength, what's the smallest possible particle that might have a wavelength. And you start thinking about the electron. Okay? Now, question 22 is a little bit more complicated, so let's actually work this out. Determine the wavelength of an electron that has been accelerated through a potential difference of 100 volts. So I know the charge of an electron is 1.6 times 10 to the negative 19 coulombs. Mass is 9.11 times 10 to the negative 31 kilograms. Potential difference is 100 volts. First, let's figure out what's the speed. Okay, and I can set potential energy equal to kinetic energy over here. So Q delta V is equal to 1/2 mv squared. So the velocity of the electron is equal to 2q delta V over m square root, which is equal to 5.93 times 10 to the 6th meters per second. Okay, so now that we know the speed, what's the de Broglie wavelength? So with the Broglie wavelength, we will set our two momentum formulas equal to each other. So lambda is equal to h over mv, 6.63 times 10 to the negative 34 joule seconds, divided by 9.11 times 10 to the negative 31 times 5.93 times 10 to the 6 meters per second, which is equal to 1.23 times 10 to the negative 10 meters. Now, that still seems like a small number, but understand that's not a number that's outside of humans' realm of understanding. When you talk about viruses, when you talk about organelles, proteins, this is the scale of that scale. And because of this idea that this wavelength is on that scale, scientists actually were able to create electron microscopes that are over 1,000 times more powerful than regular light microscopes.
An electron is a tiny bit of matter, like a tiny marble. Let's fire a stream through one slit. It behaves just like the marble, a single band. So, if we shoot these tiny bits through two slits, we should get, like the marbles, two bands. What? An interference pattern! We fired electrons, tiny bits of matter through. But we get a pattern like waves, not like little marbles. How?
So the fact is that, there's been lots of evidence that shows that electrons do have the ability to act like waves. That was just an animation, but when scientists then sent the electrons through a salt structure, the electrons, squeezed through a salt structure and they interfered with itself. And you can see with these bright spots over here on the detector that there was an increased concentration of electrons at those locations rather than an equal dispersal simply because of that interference pattern. So over here is just a quick scale. Now, normally with a light microscope, visible light, we can see things as small as bacteria. We see, certain cells, but if you've noticed, we're never able to really look that closely at things. The fact is, anything that's smaller than the wavelength of light, well, we can't really see clearly. It becomes fuzzy, okay? So the great thing about electron microscopes is that they work on a scale of, well, over here. So almost small enough to really see the atom itself, but really it's large enough to see, it's the right size to see viruses. So if you take a look in this demonstration over here of how an electron microscope really works, they have a device that focuses a stream of electrons that shoot down. And even the little particles, they are acting as waves at the same time. And they collide and bounce off of whatever's on the slide, just like with a light microscope. And after it bounces off, you have a detector that just measures how they bounce off. And once they bounce off, the detector takes a picture, and we get these amazing images of, this is actually the surface structure of a cell over here, okay? And normally you can't see things that closely, but we're looking at the actual proteins themselves.